Hi everyone, welcome to Network Security. I think this is the lecture number 13. So today we're going to talk about very interesting topic, which is digital signature. All of us know signature, real signatures. We have used them. That's how we write our checks, documents, and all of that. But in the e-world, you have to use a digital signature, and it's a mechanism for security. So we'll introduce you to digital signature. We'll show you different ways how to do it and what kind of security to provide. So we're going to define to you the digital signature, then define security services provided by the digital signature. Remember, in the first lecture we're talking about services and mechanisms. We'll define the attacks on the digital signatures. Then we discuss this digital signature schemes, including RSA, Al-Jamal. So there is a few protocols that we have learned, and we know how it works, but now we use them for digital signature. Not for encryption, for digital signature. We'll talk about the Schnorr, DSS, and elliptic curves, also used in digital signatures. And then we'll talk about some applications. All right? So we'll introduce here, talking about the difference between conventional signature and digital signature. So in the conventional signature, it's included in the document. So when you have a document, you try to sign it physically, and it's part of the document. So signature always part of the document. You cannot have signature and document separated. They are part of the document. But when we sign a document digitally, we send the signature as a separate document. So document sent different than the signature. So signature is kind of a different document, right? So for verification, to verify the signature, in the conventional signature, when the recipient receives a document, the person will look at the signature in the document and compare it to another signature in the file. So it looks at the two signatures are equal, okay? There is expert people to compare the signatures. However, in the digital, it will receive, the message received separate from the signature, and to apply the verification, verify it's a true signature, you have to use a digital way for verification, to verify the signature is true, right? So the relationship for a conventional signature, there is normally a one-to-many relationship. So one signature, so usually you as a person might have one signature for all the documents in your life, right? One signature. However, in the digital, and here we're going to have one-to-one relationship. That means every document will have a different digital signature. Okay? So it's one-to-one. Okay. When it comes to the duplicity, in the conventional signature, a copy of the signed document can be distinguished from the original one on the file. Okay? It could be distinction. In the digital signature, there is no such distinction unless there is a factor of time on the document. Factor of time in the document. All right. How we process digital signature? How we do process the digital signature? Okay. So digital signature in here, the digital signature process. So usually you have a message that you need to sign digitally, right? So you're gonna pass it to a signing algorithm, okay? And then you're gonna send two parts, the message itself with the signature, all right? So the message here could be encrypted again, it could not be encrypted, doesn't matter, okay? What matters, I need to make sure that the message is signed by Alice. When it's received, it's gonna go to a verification algorithm, all right? And Bob will be able to know that Alice has signed the document, Okay, so we have the message and the signature are transmitted. They are two separate entities. Okay, it's not one document, right? So, how we do that? We need keys for that. We need keys. So adding keys to the digital signature process. So you have in here the message, and you have Alice's private key. So the only person knows the private key is Alice, because it's her private key. So she will sign it with the private key. Okay, sign the message, sign it, and then it will send the signature with the message. When it goes back, the message will be received, and with Alice's public key, Bob will be able to verify the signature. Okay, if he can, signature is a file, right? It is a message, right? Another message. So if you can unhook it and you know with the and encrypt it with the public key, then that verifies it. All right? Okay. Remember before, this is like this is a asymmetric key, right? Public and private key. For encryption, what we used to use? Public key of Bob to encrypt. So Bob is the only one can read it. All right. In here, anyone can read it. Bob, George, Steve, as long as they have the public key of Alice, right? So a digital signature needs a public key system, asymmetric system. Okay. The signer signs with her private key. The verifier verifies with the signer's public key. Public, and so we start with the private key of the sender, and we verify it with the public key of the sender. Again, for privacy, we did not use the sender's pair. We used the receiver's pair, right? All right. So a crypto system uses the private and public keys of the receiver. A digital signature uses the private and the public key of the sender. So we could use them together now for privacy and for signature. For privacy and signature, we could use them together. So what we'll do in here we could create a digest. So from the message, we could create a hash. All right, and we don't sign the whole message, because when you sign the whole message, that means encrypting it. So what if the message is so big? It's gonna take longer time. Why do I need to sign the whole message? I create a hash, and the hash will give us a digest. And for last class, the digest is a small size, right? Smaller size, 5 to 12 bits, for example, whatever, 160 bits, 128 bits, whatever it is. All right, and I will sign the hash, not the message. So I send the message as it is. When I receive it, I hash it again, I create a digest, then I verify the signature on the digest. So that will speed it up. Will speed it up right away. So signing the digest. All right. All right. So let's take a look at the services. So we discussed several security services in the very mechanism and services in the very first chapter, if you remember. Okay, so what we spoke about: message confidentiality. So that's encrypting the message to be confidential. Then we spoke about non-repudiation. What is non-repudiation? That the sender and the receiver cannot claim, I did not send it. No, I did not receive it. So they cannot deny that. All right. And then also, confidentiality is a secrecy. Message authentication by using digest. So the message is not altered. Authentication means not altered. So what we did last time in previous lecture, we created a digest. So when the message is received, we check the digest again. If it's the same, then the message is authentic. Right? So remember when I told you that there is a difference between message confidentiality and between authenticity. So if I tell you next class there is exam, this message does not need to be confidential. It needs to be authentic. Authentic means it's coming from me. So, you know, and then message integrity, also the message did not alter. We use a hash for it, and then non-repudiation. So these are 4 services. All right. So digital signature can directly provide the last 3 except confidentiality. It does not provide confidentiality because it does not encrypt the message. Okay. So if we need to have confidentiality, then we have to use either symmetric or asymmetric encryption with it. All right. So again, digital signature provides you with what? With authentication, message authentication, with message integrity and non-repudiation. Okay, 3 services out of 4. So let's talk about message authentication. So a secure digital signature scheme, like a secure conventional signature, can provide message authentication. So when it's signed, it's authentic, coming from that person. Why is it so authentic? Because the person signed it, and you can't verify that the person has signed it. Right? So digital signature provides a message authentication. Agree?
Yeah.
Right. Then also message integrity. It provides a message integrity. That means the message is integral, not altered. How that happens? The integrity of the message is preserved even if we sign the whole message, because we cannot get the same signature if the message is changed. How we regenerate the signature? In the original message. So if the message has changed, can we generate the signature again at the receiver? We cannot.
Okay.
So you send the message. If the message is the sent message equals to the received message, then the signatures will be equal.
Yeah.
If it was altered, the signatures will be
This one.
different.
Yeah.
Alright? Alright, so digital signature provides message integrity. So it's very nice. I mean, like 3 services out of 4, you always could achieve with signature. So wondering why we don't sign all our documents, right? Sign all our documents. Alright, non-repudiation, okay, which is denial. So look in here what we do. Okay. So Alice has a message. We sign it with Alice's private key. Alright? So signing the signature, signing algorithm. So what I will have, I have the message and the signature by Alice. Then it goes in here to trusted center, or trusted center. So in here, in the trusted sender, it will have the public key of Alice. So again, I go and will be verified. So who does the verification now?
Trusted center.
The trusted center. Okay, it will verify. So Alice's public key will be verified, and then the message is gonna go to signing algorithm private key of a trusted center. So you have the public key, okay, of the trusted center with Alice's to read it, and then it will be signed again with a trusted center.
Yeah.
So the trusted sender will sign it again and will send it to where? To Bob with the private key of the trusted center.
Yeah.
Alright. And it will be received and decrypted. So can Bob deny he did not receive the message? No,
No.
because it went through the trusted center. The trusted center will say, no, I have sent it to you. And
What makes trusted center trusted?
trusted by all the parties. It's like a governmental institute, place. Okay, so trusted by everybody. Okay, so everybody gonna go through the trusted center. Yeah,
Can the trusted center be compromised?
everything can be compromised, including you and I. Okay, so that's, everything could be compromised, but supposedly no. So this is like a governmental, like a, entity that for the whole country or the whole world that is trusted, trusted whole world.
Can it be
a non s- l- the trusted center now, like sending a mail to somebody, how will you tell the trusted center in a mail conversation? Because
How-
you're not. You said it's a governmental organization,
Mhm.
but in conversing with someone, exchanging of mails, where is the trusted center in such intermediary?
Well, I think what he's trying to say is how the job of the trusted center, is it visible to both the sender and
Yeah.
receiver?
For everybody. So we subscribe. So let's say I am a law firm and you are my customer, right? Okay. So we'll agree that any communication has to go through this trusted center. So trusted center is trusted. Okay, by everyone, trusted by the government, trusted by the court, trusted by everybody. So whenever I need to send you a private message, sign a message, I don't send it directly to you. I send it to the trusted center. The trusted center will sign it again and send it out. It's kind of like double signature.
So that means, so basically in our emails now, it means there's a kind of signature that the trusted center has confirmed it or has
The
authenticated.
trusted center is like a trusted center is a center that has two keys, public and a private. So always you could use the public key of the trusted center to verify it.
Which one they have access to the information?
Hmm?
The trusted center, they have access to the message.
It has no, well, you don't have, has nothing to do with this discussion because the message could be also encrypted. So if the message is encrypted, okay, then then it's encrypted. The trusted center does not need to know about it. All right. So think about, for example, you have a message in here. You could sign the digest, not the whole message. All right. So in here, what you are sending to here, not the message, the digest. So the message is signed, or the digest of the message is signed by who? By the Alice's private key. In the trusted center, the trusted center has the public key of Alice and the public key of Bob. Okay, so decrypt with the public key of Alice and encrypt with his own or her own private key. All right, and the whole world knows the public key of the trusted center. Okay, as simple as that, and it's not very complicated, right? Message is different story. So the message could be encrypted. Okay, encrypted with what? With Bob public key. So the only person can read it is Bob. Why? Because Bob has its own private key. Or it could be encrypted with a shared key. Shared key between Alice and Bob. So that's a different issue. So confidentiality, remember in digital signature we said it could provide the three services except one, which is confidentiality, that you need to have a selected. So non-repudiation can be provided using a trusted party. Okay, a trusted party. Now we'll come for confidentiality. I mean, that's your question, the message. So look what you're doing here. So you have the message, all right? So Alice, we use Alice's private key to sign it, okay? And the message will come in here. We encrypt it with who? Bob's public key. We send the message, which is encrypted. What we encrypted in here, we encrypted both the message and the signature. When it comes to Bob, what we do, we decrypt it using Bob's private key. Then again, what I'll have, the message and the signature. Then after that, I take the message and I do the verification. So I cannot achieve confidentiality by digital signature. I have to have encryption. Whether asymmetric or symmetric doesn't make difference. Okay. We could have encryption not using the public and private key. We could have one key, shared key. Okay, we could do that, right? All right. So attacks on digital signature. Is there attacks on digital signatures? There's a few attacks. There's different types. of attacks could happen. And is it clear how it works, digital signature?
Yes.
Okay. I think it's very easy, very simple. So, so there is three kinds of attacks. There is key only, known message, and chosen. Key only attack and known message attack and chosen message attack. So in the key only attack, for example, Eve has access only to a public information released by Alice. Okay, Eve is always, even our examples is the bad person. So
Eve.
Alice is a good sender, Bob is a good receiver, Eve is a bad person. So if Eve, for example, can have public information about this, to forge the message, Eve needs to create Alice's signature to convince Eve that the message. So Alice has to know the signature, has to create a signature for that. Okay. Also, you could have known message attack, and you have chosen message attacks. All right. That's for attack types. So there's three types of attacks, okay, which is by key only attack, known message attack, and chosen message attack. For forgery types, there is existential forgery and selective forgery. Okay, the existential forgery, Eve may be able to create a valid message signature digest pair, but not one that she can rely on. Okay, and also you could have the second one, the selective one. Okay, and which is very negligible, very little. So yeah, there are some attacks possible there on digital signature, but they are not that strong. Let's take a look at digital signature schemes. Okay. So if you look back, let's go take a look back. In here, we need to take a look at in that box, inside this box. What we have inside that box is scheme for signing, how we sign. All right. So for that, what we're gonna use? Any algorithm, any asymmetric algorithm. What does it mean? Asymmetric, public and private key algorithm. Okay. Examples. RSA, for example, right? Okay. Al-Jamal. Okay. Elliptic curve. We studied them before.
Yes.
Okay. Any one of them will work. Any one of them will work. All right. So several digital signature schemes have evolved during the last few decades. Some of them have been implemented. So, for example, the RSA is the most common digital signature scheme. Okay. So the general idea behind RSA digital signature, what we have, if you remember, we have to generate a public and a private key. All right. So, for example, we have the message, and then we have the Alice's public key, which is EN, and D Alice's the private key. So we have to sign with Alice's private key. So you have the message, EN, okay, DN, the private key. Yes, you have to sign with a private key. Okay, this is by mistake, by the way. It should be D in here. I think it should be D because that's a private key, right? You sign, okay, and then you generate the signature. You send the signature, and then you try. So D should be here, E should be here. All right. And then you try to verify it. So the signature, you pass it to the function. If the result is equal, then accept the message. Why? Because it's verified. If it's not, reject it. All right. So, like we use RSA. So the sender and the receiver have to have a public and private key pairs. They have to find a way to share it and use it for signature. Simple. Huh? How we calculate E and D, we learned that before, right? The other thing is the key generation. So the key generation in the RSA digital signature scheme is exactly the same key generation in the RSA. So if you know how RSA works, you know how to generate keys, because that's a whole trick. Okay, RSA digital signature scheme, D is the private, EN is the public. Okay, pair of keys. All right. So in here, if you need to take a look at it, signing and verifying. So for example, so the message to the power of D. What is D? Is the private key of Alice, mod N, and we'll give you the signature. The message in this example, we did not encrypt it. We just send it as it is. All right. At the verification, what you'll do, you're gonna get the message. Okay, here. And you need to calculate the message again. So you have the signature, S to E. What's E is? The public key, and will give you the supposedly the same message. If the message equals to the message, then true, accept. Accept the message. If not, don't accept the message. There is no trick in here. RSA. If you know how to do RSA, you know how to do digital signature using RSA. Clear? All right. All right. So example, for example, as a trivial example, suppose remember that he asked. Remember when he asked me a question? Do we have to have to know? Can we have? I'm not sure what's your calculation.
Was very, very
So
low.
it's like so huge, you know, the keys. I mean, we try to do trivial examples here just because it's easy to calculate, right? So as a trivial example, suppose that Alice chooses P, that number. Q, remember we choose two primes, P and a Q, multiply it together, and then phi of N. You know, there's a procedure, we have learned it. I'm not going to go over it now. So P equals 823, Q equals 953. And we calculate N, multiply this by this will give you N. And then phi N, Q minus 1 multiplied by P minus 1 will give you Qn. Now we choose E, 313, and we calculate D, became this number, okay? At this point, key generation is complete. RSA, simple RSA, we generate the keys, all right? Now imagine that Alice wants to send a message with a value of M. This is M, the message, to Bob. She uses her private exponent. What is a private? It's D in here. So what you do, this is the message, the signature is the message to the private key, mod N will give you what? The signature. What's the signature? 210625. Now the signature will be received by Bob. Bob used Alice's public key. You see, this is the signature in here, 210625, we put it in here. To the power of the public key, 313, mod the N, gave you what? 784319, which is in here, which is? Mod E, the N, and that will give you the M, how much, what is the M? 19070, which is the same message was sent. RSA. RSA. Alright? Okay, Bob accepts the message because he has verified Alice's signature. Alright? Now, that's why we said that we don't try to sign the whole message because it will be a very huge process. What we do, we create a digest out of the message, sign the digest. Alright? It's exactly even in the document, real document, when you sign the document. Do you sign it all? Do you write in all of the document? No, you a small area you sign it that you know that is still in the same document. Okay, if the document is like multiple pages, you put initials and then you put the signature, right? Okay, think about like that. So RSA signature on the message digest. Okay, so what we do in here, Alice message will create a digest using one of the techniques learned from the previous two lectures. Right? Okay, any one of the techniques. SHA-1, SHA-5, MD5, right? Okay, you have the digest, then you sign the digest, send the signature. Right? And before you start calculating the signature, you have to regenerate the digest again. So the sender and the receiver has to agree on the digest. I'm sorry, on the hashing algorithm. Alright, so this is also will give you more security. So when the digest is signed, instead of the message itself, the susceptibility of the RSA digital signature scheme depends on the strength of the hash algorithm. The stronger the hash algorithm, the more secure it is. So don't use a very weak like MD2. Use SHA-512 for example. Use, okay, for creating the hash. right? So it becomes the strength of the hashing function, right? Then one of the techniques we have learned for asymmetric is al-jamal, right? So if you remember al-jamal, it creates like two strings, right? Two strings, and so two strings, right? So what you'll have, S1, S2 is the signatures, M is the message, then E1, E2, P, okay? Just go back to al-jamal, it will gonna create S1 and S2. When you send it, okay, S1, S2, and E2 and P, okay? Remember here F1, F2, F3, and F1 is repeated in here. F1, these are equal with different parameters. If the results are equal, okay, if they equal, then accept. If not, don't accept. It's al-jamal, okay? Al-jamal protocol that we have learned before. Okay, for the key generation, we have learned how to generate keys for al-jamal last time. Just go back to that. The key generation procedure here is exactly the same as the one used in a crypto system. So in al-jamal digital signature schemes, E1, E2, P is Alice's public key, D is her private key. Just generating a pair of public and private keys. Alright? Verifying and signing. So let's in here, the same thing. So in here, you have the message. You create. Remember, in al-jamal, not one signature, not one value, two values, S1 and S2, right? So the way you create S1, that's how it is. The way you create S2, that's how it is. Okay, and then the message. You send them again, you verify it, okay? If V1 equals V2, then it's true, accept. If not, reject. Right? So in here is a trivial example. Alice chooses P, this value, E1, this value, D is this value, and calculates E2, this value, according to the rule of al-jamal. She also chooses R to be, remember that in al-jamal you have to use a random number. The sender has used, a random number, 307. Okay, it will announce E1, E2, and P public. She keeps D as a secret. The following shows how Alice can sign a message. So the message is 320. So we create S1 and S2. Okay, according to the equations we know, S1 will be this value, 2083, S2 will be 2005. So when we're transmitting what we are going to transmit, S1 and S2. Then we calculate V1 and V2, okay, and V1 and V2 3006, 3006, which is it's in here, the V1 and V2, so they are equal. Okay, that means the message is authentic. All right. Now imagine that Alice wants to send another message M3000 today to Ted. She chooses a new R107. Alice sends S1, S2 to Ted. Ted uses the public key to calculate V1 and V. So M will generate S1, S2. This will be 2732, 2526. Then you create V1, V2. They are not equal. Oh, they are equal here. Then it's an authentic message. Alright, so we use RSA, we used al-jamal, which is our regular applications that we have used. There is something called the Schnorr digital signature scheme. Okay, the general idea behind the Schnorr digital scheme. So again, you have S1, S2 signature and message. You have the public key, you have the private key, and you have the random. Alright, so you create S1, S2, what you are sending, S1, S2, and the message E1, E2, P. Alright? And for the functions which defined by the Schnorr, you calculate the function, then the hash function, and then you compare it to S1. If they are equal, you accept it. If they are not equal, then you deny it. Alright. For key generation, okay, Alice selects a prime P, that's for Schnorr. Alice selects a prime P, which is usually 10 to 24 bits and left. It has to be a very long for security, right? All right. So choose a prime. Then Alice selects another prime Q. Alice chooses E1 to be the qth root of 1 mod B. And Alice chooses an integer D as her private key. Alice calculates E2, which is E1 to power D1P, and Alice's public key will be E1, E2, PQ, and then D will be the private key. So in the short digital signature scheme, Alice's public key is this, and the private key is this, and just you apply the function 1, 2, and the 3, 1 and 2 in the sending, and 3 in the receiving, right? Process, okay? So what's the key in here? What is the most important task? Generating the keys. Anything else is application. Is an application, right? Alright, so for signing and verification in here, so you have Alice, the message, okay, using the D, which is the private key, and R is a random number. You're gonna generate S1, S2, and you send them, and now you create the verification, you compare it with S1. If they are equal, then you accept. If not, they not. This is an example, you can take a look at it. Then digital signature standard DSS. Okay, again a fourth technique. Again, DSS is the same thing, is generating S1, S2, the message. The Alice's public key is E1, E2, PQ, and the private key is D. Okay, and R is a random number. So you could generate S1 using the function 1, E1R, which is a random number, PQ, and then you're generating the S2. You're sending everything, S1, S2, E1, E2, PQ, and the digest, and you try to, you use function 3 to generate the verifier. You compare it with S1. If they are equal, then they are, the signature is correct. All right. Again, we are using algorithm. So again, where's the key in here? Is how to generate the keys and apply the algorithm. Okay, as it is. All right. So this is for key generation. The same thing in here, same thing in here. All right. So when you compare DSS versus RSA, computation of DSS signature is faster than computation of RSA signatures when using the same prime. So if you're trying to use the same prime, you start off with one prime, RSA is slower than DSS. And DSS versus Al-Jamal, DSS signatures are smaller than Al-Jamal signatures because the Q is smaller than P. Just, different comparison. Then the last one is elliptic curve digital signature. Again, it's asymmetric system. Just you have to know how to use it. So again, you're gonna generate S1, S2, and you send the S1, S2, the E1, E2, the PQ, and then you calculate the verifier, compare it with S1. If they are equal, then accept. If not, okay. So nothing new. You have to know these protocols, how they work. We already explained that in a previous lecture. Okay. Same thing. How to verify? Again, verify the signature. So there is a variations and applications. Okay. So we'll talk about briefly discuss variations and applications for the digital signature. So what we learned so far, okay, what is digital signature? Is a technique that uses asymmetric algorithm, one of the asymmetric algorithm. Okay, we sign with the private key of the sender, and we verify with the public key of the sender. We could sign the whole message, slow. We could sign the digest. Okay, good. Okay, the strength of the mechanism becomes the strength of the hash function that you are using to create the digest. All right. So basically, what we have used 5 or 6 or 4, I forgot, of the algorithms that we have learned before. Okay. The question is why you're gonna use RSA or Al-Jamal. We discussed that before. Some of them are faster. Some of them are more secure. Okay. Some of them are easier to implement on hardware than software, etc., etc. That's a different discussion, right? All right. So, so there's issues about, you know, how people can hack or verify and all of that. So all you should have like time-stamped signatures. Okay, so before in the previous slides and techniques, we did not mention the time. We just signed the document. So can we have a timed document that we sign? That means we know when we signed it, all right, for different reasons. So sometimes a signed document needs to be time-stamped to prevent it from being replayed by an adversary. So you understand? So it has to be timed, you know, at that time. So for example, if I send you a message, I tell you Thursday there is no class. Okay, if I don't time it, if I time it with today's date and time, you know it's next Thursday. But if I don't sign it, somebody could send it to you again after 2 weeks. So you will think it's valid. Why? Because there is no timing. When I say this Thursday, how many this Thursday there is? The coming one, right? Right? You understand? So it's good to include time. And also there is something called a blind signature. Sometimes we have document that we want to get signed without revealing the contents of the document to the signer. Okay? Like what? Notary public. When you go to notary public, anybody done notary public before? When you go, the notary public, he's not supposed to read the document. You're supposed to sign in front of him, and then he put his signature that this person with this driver's license came at this time and signed this in front of me. Okay, that's what's notary public. He does not verify the document, he verifies what? Your signature, right? So that's like a blind, you know, blind. So these two things, it's always good to have. All right. So that's why we could have something called certificate authorities, the CAs, that are responsible to provide these this kind of verifications. Okay, we could include time and so that's what I wanted to cover for today about digital signature. It's a very nice approach. It could achieve 3 of the 4 services, and we have seen how we could add the 4th services by encryption, symmetric or asymmetric. Any questions? All right, thank you so much.